Hey, welcome to our next lesson. Today we're going to be talking about polynomial basics. In a previous algebra course, you would have learned a lot of this stuff, but we're going to be taking it a little bit deeper and applying other things that we know to polynomials. So our mindset message for today is that struggle grows your brain. Some of the stuff in this next unit we're doing may be challenging, or even in this very first lesson, but you can do it, and you got to realize that it's literally true that your brain grows when you work through the confusion and the struggle. Our learning goals today is to, first of all, just identify a polynomial and its parts, and then perform operations on polynomials, both of which technically should be review, but we'll still go through that. And our main prior knowledge would be just what is a polynomial. Using the zero product property, this is something that we're going to use through the whole next topic we're studying for a while now, okay? So this is like, if I have an equation like this, I can utilize this property. If we multiply two things to make zero, well then one of the things must be zero. So in the x value to make this factor be zero would be positive 2. The x factor to make this factor zero would be negative 5. Multiplying using expansion boxes, and then what is an identity equation? That's something that you should be familiar with, but maybe you forgot. An identity is just an equation that's always true. In fact, I should have put that here. It's an equation that's always true, aka it has infinite solutions. So an example would just be, we know x times x plus 5 is always equal to x squared plus 5x. Because that's how distribution works. So since this equation is just always true, it's called an identity, okay? So the thing about this is, technically the behavior is different. What we're saying here is, if I take a number and then multiply it by 5 more than himself, that's exactly equal to squaring the number and adding it to 5 times himself, which actually is kind of a surprising thing if you think about it. It's a totally different sequence of steps, but it's just always going to produce the same results if you put a number in there. So let's get to a couple of vocab words. And again, these should be review. A monomial is a product of a number and one or more variables to an integer power. Now, we're mostly focusing on just one variable in high school. You don't move to multiple variables very much till you get to college level stuff. And a polynomial, you know mono is the prefix representing one, and poly means many, right? So it's simply the sum of one or more monomials. Sometimes people are confused and they think a monomial is a poly because it's still just one, but it still kind of counts. Let's look at an example of a polynomial real quick and then dive into some more things. So here's a quadratic expression, and we should be pretty familiar with these at this point. We know that that this has the sum of different parts. Now, each of those parts is a monomial, but we also call it a term. And technically, this one here doesn't have a product of any variables with it. And you can think about it like this. If you remember from your exponent rules before, anything to the 0 is 1. Technically speaking, this is x squared, x to the 1, and x to the 0. Because anything to the power of 0 is just 1. So that still counts as a monomial, actually. And this power of 1, we typically don't write it down, right? So this is just some vocab to remind you guys. This whole thing is considered a polynomial because it's made of multiple, well, it's at least a monomial anyway. The numbers in front of the variable are called coefficients. The highest exponent in the whole thing, now if you write it in normal form like this, it's going to be the exponent on the leading term. That's called the degree. So this is a degree 2, and we've learned that a degree 2 polynomial is called quadratic. And if it's degree 3, it's cubic, and if it's degree 1, it's linear. Okay, but we'll use those frequently enough that you'll grab onto that. Okay, and then this one here, because it stays constant, we also call that the constant term. There are two important ways of viewing polynomials. The first way, and this is really important by the way, is as an expression. And it doesn't necessarily have any particular meaning or connection to something, but we can work with it by factoring, simplifying, or combining it with another polynomial, let's say. But you can also think of a polynomial as a function. And a function, remember, is like a machine. It takes inputs and it applies it as a rule, and then it turns the inputs into outputs. All right? So here's kind of a warm-up for you to do yourself that highlights these two things. If this is like A and B, then this focuses on expressions, and then here focuses on it more as a function. So pause right now, please, and work on these yourself, and then we'll come together and check them. Okay, let's check our work. The factored form of this would be 3x minus 5 times x plus 4. And remember, you can always multiply this and expand this out to check your work for those, right? Another reminder, this and this are exactly equal. It's just like we talked about here as an identity equation. So if we said this equals this, that forms an identity. Okay, so there's the factored form. Add it to x squared minus 2x plus 11. If you recall, maybe the easiest way to add two polynomials is like line them up so that you have the like terms aligned, and it's just like place value if you think about it as strictly as a number. You have your hundreds or thousands lined up with each other. Okay, so if we add these, our x squareds make 4x squared and then down the line. So 4x squared plus 5x minus 9. And let's say this had a different term, like if it had a cube term on there and this didn't, that's okay. When you add them, whatever this was just stays along for the ride. Now we'll focus on them as a function. So if we call this f of x, this says find f of negative 2. So here's the calculation. You can just check that. Negative 22. And then last, this one might be a little weird because we're putting an expression in, a separate expression in as an input. But that's okay, because this just says 3 times input squared. And if our input is m plus 3, then it's 3 times m plus 3 squared, plus 7 times input, minus 20. And I did not have enough space to put it in normal form, so let's use this, because this example will be helpful as we transition to the next thing, and I'll finish this off with you in the next segment. So here's the last part of our previous example. Our original function, f of x, was 3x squared plus 7x minus 20. If I wanted to find f of m plus 3, remember how we set that up prior. And at this point, we just simply need to simplify it. M plus 3 squared, be careful, don't perform this grave error that people do. You cannot distribute exponents. You have to take m plus 3 times m plus 3. And that gives us m squared plus 6m plus 9. So finish off checking your work for this, okay, if you need to. Double check that this is what you got. One important thing I want to talk about here, and this is kind of an advanced thinking from our previous understanding of polynomials, is identifying what's the base of the polynomial. Okay, and when I say the base, it's not like exponent bases, I just mean like what's forming the foundation. So in this case, our variable, I guess, our base is x. So we say that it's a polynomial in x. The weird thing here is, this is the same polynomial, but we could consider our base, our foundation, as m plus 3. So we could call this a polynomial in m plus 3. And it's weird to think of m plus 3 as its own thing. But remember, we've done substitution before. You can think of this as another variable like y, right? And then simplifying all down along the way, we could just say this one's simply a polynomial in m. So that's just the vocabulary we use. Now, I'll remind you, polynomials only have to have integer exponents and not negative. So it has to just be positive whole numbers as an exponent to count as a polynomial, or technically 0. So just a quick thing, answer this for yourself and pause. Is it a polynomial in x? Let's see how you did here. Remember, a polynomial in x has to have whole number powers, and it's just the sum of a bunch of monomials, right? Which is just numbers multiplied by variables, right? So, this right here, yeah, it's a polynomial. B, careful, because this is dividing, not multiplying. But another way to think of it, this is going to remind you of some exponent rules from your past, which actually maybe I should have put that in our list of prior knowledge as well, as exponent rules, so you can add that in there. However, 5 over x is the same as 5 times 1 over x. And we've learned that 1 over x is equivalent to saying x to the power of negative 1. Now don't worry if you don't remember why that works. We'll learn that again later this year. However, just realize this is dividing, but it also means it's a power of a negative number, but we only can have 0 or positive whole numbers as the power. Part C, yep, quadratic, we know that it works, yes. Part D, it's tempting, but that square root, what's going on with that? Another thing, hopefully you remember from your past, is that a square root is the same thing as a power of 1/2, which is not a whole number, so that means it fails the polynomial test, right? E, we have x cubed plus 30 to the x, but the one thing problem here is we cannot have an exponent that's a variable. The exponent has to be just a number, and again, a non-negative whole number. And then this guy right here, basically the same reason as part B, he is not a polynomial. One quick comment to go in with what we talked about up here on part F just now is definitely, we said it's not a polynomial, but it depends on what we're using as our base, our foundation, right, our variable. It's not a polynomial in x, right, because we're dividing by x. But if you mess with this just a little bit, you can see that it's the same as this, and we basically have something squared plus 3 times something to the 6th, which that structure is a polynomial, but it's a polynomial in 1 over x. That whole concept there, I know it's a little tricky and weird. It's not the biggest deal right now, but it's something important to keep in mind and mention, and it will help with some stuff we're going to be doing soon. Let's move on to just one more example before we're wrapped up for today. Okay, so this last example, again, is just more practice focusing on these two aspects of polynomials, as expressions as well as functions. So go ahead and pause, and I want you to do these on your own, and then we will finally come back and check our answers together to end this lesson off. Alright, so let's check our work. My preference to multiply this out and show its equivalent would be to use an expansion box to help organize the distribution. I want to remind you guys, when you use the expansion box here, each of these kind of represents area, so then the full total product is the sum of all the pieces. And I've color-coded the like terms. They're always going to be on a diagonal like this, so again, this is a very useful organizational tool. In the end though, if you add all these separate pieces together, you're going to see that it's the same. This one's interesting because the way I set this up here, if you plug 3 in for x, this becomes 0, and no matter what that is, 0 times anything, that's why I just put stuff here. I don't even care what that is because that became 0. So that just gives me 0. Now, it's a little bit more work to do the other one. That's why certain formats of functions or expressions can be more useful sometimes than others. But if I plug it in directly to this one that's in normal form, then we have to do all the calculation, but in the end it still works out to be 0. So that's nice. And then last, subtract f of x minus h of x, and then here's that function. So similar as we did before, line up the like terms. You'll notice something though. I have dropped the degree. Even though the original two have degree 3, they're cubic, when I subtract them, because the leading term is exactly identical, the result is quadratic. And that sometimes can happen. But anyway, there's your answer for that. So that's it for this lesson. It was very much a review and warm-up lesson. So happy math, and we will see you next time.